Hello everyone, this is Youth Anusri from CSIT. Today I'm going to tell about a rapid prototyping approach for high performance density based clustering from data mining and knowledge discovery. Introduction. Clustering, a fundamental technique in data analysis, plays a vital role in uncovering hidden patterns and structures within datasets. Traditional clustering algorithms have served as well, but as the scale and complexity of data continue to grow exponentially, there arises a need for more efficient and high performance approaches. Today, we dive into a groundbreaking innovation, a rapid prototyping approach for high performance density based clustering. This approach represents a shift in the realm of data science, offering accelerated methods for identifying dense regions in large datasets with remarkable speed and accuracy. In this presentation, we will explore the motivations behind this approach, its underlying methodology, and the significant impact it holds for various applications in fields such as machine learning, pattern recognition, and data mining. The challenges posed by traditional methods and the promising prospects offered by the rapid prototyping approach. Density based clustering focuses on identifying regions of high density within a dataset separated by areas of lower density, unlike traditional methods that require specifying the number of clusters beforehand. Density based algorithms can discover clusters of arbitrary shapes and sizes, making them particularly well suited for datasets with irregular distributions and varying densities. At the heart of density based clustering lies the notion of density reachability or density connectivity. Points are considered part of the same cluster if they are sufficiently close to each other and if the density of neighboring points exceeds a certain threshold. This introduction provides a concise overview of density based clustering, highlighting its advantages over traditional methods and emphasizing its ability to handle complex data sets. It sets the stage for further explorations into the topic. Research objective. The primary objective of our research is to develop and validate a rapid prototyping approach for high performance density based clustering algorithms. Specifically, we aim to enhance the efficiency and scalability of existing density based clustering techniques by introducing novel prototyping methodologies. Address the limitations of traditional clustering algorithms such as sensitivity to parameters, settings, and computational overhead. Explore the potential applications of rapid prototyping in real world scenarios, including but not limited to anomaly detection, spatial data analysis, and pattern recognition. Evaluate the proposed approach through comprehensive experiments on diverse datasets, comparing its performance against state of the art methods in terms of clustering accuracy, runtime efficiency, and scalability. Through this research, we seek to advance the furniture of density based clustering, providing practitioners with robust tools for effectively analyzing and interpreting large scale datasets in various domains. DeepScan and clustering in machine learning. Clustering analysis, or simply clustering, is basically an unsupervised learning method that divides the data points into a number of specific batches or groups, such that the data points in the same group have similar properties and data points in different groups have different properties in some sense. It compromises many different methods based on differential evolution. Example, k-mean distance between points, Fluid propagation, graph distance, mean shift, dB scan, distance between nearest points, mixtures, picture clustering, etc. Fundamentally, all clustering methods use the same approach. First, we calculate similarities and then we use it to cluster the data points into groups or batches. Parameters required for DB-scan algorithm. First, EPS. It defines the neighborhood around a data point, that is, if the distance between 2 points is lower or equal to EPS, then they are considered neighbors. If the EPS value is chosen too small, then a large part of the data will be considered as an outlier. If it is chosen very large, then clusters will merge and majority of the data points will be in the same clusters. One way to find the EPS values based on the k distance graph. To PTS, minimum number of neighbors within EPS radius. The larger the dataset, the larger value of min PTS must be chosen. As a general rule, the minimum can be derived from the number of dimensions d in the dataset as greater than equal to d plus 1. The minimum value of the min must be chosen at least 3. This diagram shows the density based clustering. Overview of proposed rapid prototyping approach. Our proposed rapid prototyping approach for higher performance density based clustering involves several key components aimed to accelerating the clustering process while maintaining or improving its accuracy and scalability. Initial prototype selection. We begin by selecting a small subset of data points as initial prototypes, utilizing techniques such as random selection, density based sampling, or K means clustering. Step 2, prototype expansion. The selected prototypes are then expanded iteratively by incorporating and neighboring points based on density and distance criteria. This expansion process aims to capture the underlying structure of the density efficiently. Dynamic parameter adaptation. To adapt to varying data characteristics and densities, our approach incorporates dynamic parameter adaptation mechanisms. This ensures robustness and flexibility across different data sets without manual tuning. Parallelization and optimization. Leveraging parallel computing architectures and optimization techniques, we accelerated the clustering process, enabling efficient processing of large-scale datasets with reduced computational overload. Incremental prototyping. As new data becomes available or streaming data is encountered, our approach supports incremental prototyping, allows for real time updates and adaptation to evolving data distribution, evaluation, and validation. Finally, we conduct rigorous evaluation and validation experiments to assess the performance of our rapid prototyping approach in terms of clustering accuracy, scalability, and runtime efficiency across various benchmark datasets. Through these innovative strategies, our proposed rapid prototyping approach aims to density-based clustering provides researchers and practitioners with powerful tools for rapid and accurate data analysis in diverse applications domain. Overview of proposed rapid prototyping approach. Metrics for evaluating clustering performance. When evaluating the performance of clustering algorithms, several metrics are commonly used to assess the quality of the resulting clusters. These metrics provide quantitative measures of how well the algorithm have grouped the data points. Some of the key metrics include clustering accuracy, measures how well the clustering reflects the true underlying structure of the data. This can be accessed using external validation measures such as adjusted and index, normalized mutual information, or flawless index when truth labels are available. Intra-cluster similarity measures the similarity of data points within the same cluster. Commonly used metrics include the coefficient and an index. Intercluster separation measures the dissimilarity between clusters. Metrics such as the index and intercluster distance can be used to access how well separated clusters are from each other. Compactness and separability measures how tightly clustered the data points are within each clusters and how well separated clusters are from each other. Metrics like the within cluster sum of squares and between cluster sum of squares can be useful in this regard. Robustness and stability measures the stability of the clustering results under perturbations in the datasets or algorithm parameters. Stability based metrics such as stability index and variation of information can be used to access the robustness of the clustering. Computational efficiency evaluates the runtime efficiency and scalability of the clustering algorithms. Metrics such as runtime, memory usage, and scalability to large datasets can be important considerations, particularly for real world applications. By considering a combination of these metrics, researchers and practitioners can gain a comprehensive understanding of the performance of clustering algorithms and make decisions when selecting or designing clustering methods for their specific applications. Hardware and software specifications. When implementing and evaluating clustering algorithms, it is crucial to consider the hardware and software environment to ensure optimal performance and reproducibility of results. Here are typical hardware and software specifications. Hardware processor. A multi-core processor with high clock speeds is desirable for parallel processing tasks involved in clustering algorithms. Memory RAM. Sufficient RAM is essential to accommodate the dataset and any intermediate data structures used during the clustering process. For large datasets, a higher RAM capacity is recommended. Storage. Adequate storage space is necessary for storing datasets, intermediate results, and any additional files generated during the clustering process. Software operating system. The choice of operating system depends on personal preference and compatibility with the clustering algorithms and its dependencies. Common choices including Windows, Linux, and macOS programming language. Most clustering algorithms are implemented in programming languages such as Python, Java, or C++. Ensure that the chosen language is compatible with the algorithm and has sufficient libraries and packages for data manipulation and analysis. Development environment. Utilize integrated development environments such as PyCharm, Jupyter Notebook, RS Studio, or Visual Code Studio for coding, debugging, and visualization. Clustering libraries. Depending on the algorithm chosen, utilize relevant clustering libraries or packages such as Skitlearn or TensorFlow or Spark ML for implementation and experimentation. Additional tools. Consider using supplementary tools for data pre-processing, visualization, and performance evaluation such as Pandas, Max, and Skitlearn metrics module. Cluster computing option. For large-scale clustering tasks or compute-intense algorithms, consider utilizing cluster computing frameworks such as Apache Hadoop, Apache Spark, or Dask. These frameworks enable distributed computing across multiple nodes, significantly reducing computation time for large datasets. Ensuring compatibility with the chosen clustering algorithm and consider the scalability, fault tolerance, and resource management features offered by the cluster computing framework. By adhering to these hardware and software specifications, researchers and practitioners can ensure a robust and environment for implementing, evaluating, and deploying cluster algorithms for various applications. Applications of density based clustering, anomaly detection, spatial data analysis, customer segmentation. Customer segmentation involves in marketing and customer analytics. Image segmentation, social network analysis, time series analysis. Its applications highlight the versatility and utility of density-based clustering algorithms in solving a wide range of real-world problems across different domains. By leveraging the inherent properties of density and connectivity, these algorithms enable insightful analysis and decision making from complex and high-dimensional datasets. Conclusion. In conclusion, our research presents a rapid prototyping approach designed to enhance the efficiency, accuracy, and scalability of density based clustering algorithms. By introducing novel standards such as dynamic parameter adaptation, iterative prototype expansion, and support for incremental prototyping, our approach addresses critical challenges faced by traditional methods. Through rigorous evaluation and validation, we have demonstrated the effectiveness of our approach in achieving high clustering accuracy and robustness across diverse datasets. Moreover, the practical applications of our approach extend to various domains including anomaly detection, spatial data analysis, and pattern recognition. Looking ahead, further refinement and exploration of our approach hold promise for unlocking new fortness and density based clustering, paving the way for more effective and scalable data analysis in real world scenarios. Thank you.